Hello, everybody. Thanks for joining us today. Today, we're going to do a live demonstration of tailored waveform technology, like what this is about. We're going to show you some live measurements of, the ion energy distribution function in a plasma while applying a, sinusoidal and non-sinusoidal bias to the electrode. And we're going to show you all that live. Before I start, just everybody, if you have any questions at any point during this, please put them in the Q&A box. And after the live demo, I'll be answering any questions that have come through. Or at least I'll do my best to answer them. Today's topic is measuring tailored waveform bias plasmas. And we're going to use some impedance sensors to do that today. My name is Tom Gilmore. Co-author is Anshu, who helped me today. And down in the lab, we have Jordan and Sarah, who are going to run all the equipment when it's time to do the live demo. So go to the next slide. A very quick introduction to impedance before we get into the physics and technology. Impedance, we're a company based in Dublin, Ireland, and we were founded in 2004 by Professor Mike Hopkins. And we've 40 plus employees, plus a global distribution network. So our sensors are available anywhere in the world. And our core focus is to provide, advanced plasma and RF diagnostics, okay? Primarily to the semiconductor industry, but we also work quite closely with the university and research markets. So anyone who's doing something serious with plasma, we generally work with and help them as best we can. So at the moment, this demo, I'm sitting up here in this building, and the lab is down here where Sarah and Jordan are. And and for those of you who aren't familiar with impedance, this is our general product portfolio. But today, what we're going to be looking at, we're going to take measurements using one of our Semion systems, which looks like this, and using one of our octave suite sensors. And in particular, we're using one that looks like this. Let's get into the main topic. So the outline of today, we're going to just do a recap on plasma surface interactions. So if anyone has attended some previous webinars, you're going to see some familiar slides, but just to set the scene for what the challenge is that we're facing. And then we'll look at different methods of IEDF control, and then we'll focus in on tailored waveform. And then we'll do the live demo and showcase what we can measure in real time and how we can help with the challenges for this new technology. Okay. So let's talk a little bit about plasma surface interaction. So this is a recap from previously. And in order to understand what's going on, on a wafer surface, we have to understand, what are the fundamental processes happening on the wafer surface. Now, there are many processes happening. There's different reactions because of the neutrals, because of the radicals. There's depositions and etching that can be happening depending on the conditions. But ultimately, for many processes, what matters the most are ion energy and ion flux. These days, there are also like radical-driven processes, but today let's focus on the ion energy and ion flux. And ion energy is simply, how hard is the surface being hit? How fast are the particles in the plasma hitting the surface? Okay. And just to give you a feeling for what's happening inside chambers, if you have a grounded electrode and you're powering the top electrode, the ion energy is going to be from the plasma potential. So the plasma potential might be 15, 20 volts, 25 volts with respect to ground. So the ions are going to pick up, let's say 25 eV going from the plasma to ground. So that's going to be their energy. So that means in a grounded situation, the ion energy is going to be related to the plasma potential, okay? If you apply a bias to the bottom electrode, you're going to put a large, there's going to be some voltage which is going to attract the ions. So if you put an RF bias on the bottom electrode, you usually get much higher energies. You get a large negative DC, like on average, large negative DC bias. That pulls the ions down and accelerates them, and it etches the surface, okay? So this obviously changes etch rate somewhat. And then the other thing that matters is ion flux. How many ions per second impact the surface? Obviously, this controls how fast the process is done, okay? And some people go a bit further and calculate like ion dose, which is like how much flux over time, how much have I deposited or, on the surface, or how much yield have I etched away, like how much sputter yield have I got from the surface. So you can calculate all these things once you know the ion energy and ion flux. And just a note, like if the ion energy is too high, you might be damaging the material that you're processing. And if it's too low, you might not be doing anything at all, not functionalizing the surface. There's also some sweet spot energies for particular processes, which we'll show later. And obviously, if there's some sort of power fluctuation, this bias can change. So normally you set, I put power output on the generator. I assume that power is getting to the electrode, but in reality, the cable's heating up, the matchbox is heating up. The plasma impedance might be drifting, and that's changing the voltage on the surface. So even though you might have a fixed power at your generator output, you could have something quite variable on the plasma side. And there are other complications. I just want to focus in on this nice diagram. So you'll see this a lot in my presentations. Really, the structure zone diagram by Andre Anders is really, really insightful for giving an intuition of what's going on depending on your energies and temperature. Okay. I want to focus in on two areas. So this axis here is basically it's energy deposited to the surface, but let's say it's ion energy. So you can see, for example, here, a region of low temperature, low energy, ion-assisted epitaxial growth. So you can do some really, really precise stuff if you have the energy just right, the temperature and everything is just right, okay? So this is a really fine area where you can easily go outside of this area. I'll show you another graph that shows exactly what this is for certain materials in a minute. And then there's other areas where you can get these fine grain, nanocrystalline growth with the orientation that you want. Again, specific temperature, very specific energy is needed. If your energy is too high, you're just etching materials. If it's too low, you get a different type of growth. Okay, so exactly what's hitting the surface matters. Okay. There's also the neutrals matter, like ion neutral ratios are a thing, but let's keep on going. This is just another little diagram from this nice paper about trying to model these things. So not only do the ion energies matter, also things like ion angles matter. If you want to etch something to a particular depth and you want to do it right, you also need to make sure you have the right energies and the right direction. It's kind of a topic for another day, but what I want to discuss today all feeds into this solving the same problems here. How do you get precisely the energy, precisely the flux you need in order to make exactly the feature that you want? So let me actually go ahead a little bit. So just to show you some real examples, okay? So this is from a nice paper from Gremy, where they were measuring the etch rate as a function of the bias applied to the electrode. Okay, so this sort of data exists for a lot of materials out there. So here is etch rates in nanometers per minute and the bias voltage. Now, bias voltage is not exactly the ion energy because you have the plasma potential, but it's basically ion energy. And you can see, and this is maybe a bit obvious, if the energy is too low, you don't do anything. The material just does not etch. Okay. And then once you hit a certain threshold, you start etching the material. And then as you increase the ion energy, you increase the etch rate. Okay. So ion energy obviously has an impact on etch rate. Now, during this experiment, so when this was happening, there was a simultaneous measure of the ion energy distribution function with one of our semians. You can see here, the distribution function is really quite broad. So you have ions at, in this case, with the yellow curve, you have ions at 60 and 80 and 100 and 120 and 140, even some at like up at 150, right? So you have a really, really broad spectrum. So if you want to calculate what the etch rate is, okay, you have this data here, but you kind of have to, multiply this by this and this by this, and and you can see here, obviously, if this is showing small shifts in bias. So these small shifts in bias, so let's say you're delivering constant power, but the matchbox is heating up and less power is being delivered and your bias voltage is dropping. That means mid-process, your etch rate is dropping, right? Your etch rate is changing because the ion energy is. So the control of this and measurement of this is kind of critical. Now, you don't have the luxury of having an ion energy distribution function measurement device in situ in the chamber. So you want to have control of that from outside, like really direct control and direct monitoring from the outside. Okay. Here's just a second example with some other materials, and you see the same kind of data. This one, in this case, it is ion energy, and at different energies, you get different etch rates, different cavity sizes, this sort of thing. Okay, this is from Letty, I think. By the way, this data here. Whoops, is from a production tool. Okay, so no tool is perfect, and no matter how much you paid for it. There's always some physics going on that you should be aware of when you're doing process development. So the message I'm trying to give here is you kind of need to know what the ion energy distribution function is if you want to do any sort of modeling on what's going on in your chamber, or if you want to have any sort of fine process control for small feature sizes or for atomic layer etching or deposition. So let me just show you some basic methods of controlling the IEDF. So, these are the kind of classic methods. So, for example, if you wanted to keep the ion energies low, you could have a grounded or floating surface, and then you just change the flux by changing power on the top. Okay, fairly straightforward. You raise and lower the etch rate by raising and lower the power on the top. You basically raise the plasma density, more flux, more etching. But, as you apply more power, the plasma potential doesn't shift too much, so you're not changing the energy too much down here. If you have a situation where you have just a bottom electrode powered, the energy and flux are totally coupled. So as you increase one, you're increasing both, okay? Which can be a bit troublesome. And this is fairly common tool design. You also have the case where you have maybe an ICP coil on the top, and that's pretty much just controlling the ion flux, and then by changing the density, and you have an RF bias on the bottom that's pretty much just controlling the energy. And the lower the frequency you use, the less impact you're having on the flux. So you could, be just have an energy and flux switch. But it's still not ideal. They're still a bit intercoupled, and you're still relying on the power being consistent, where that's not really what you want. You want a direct measurement of the energy, the voltage, okay? I showed you this before, but this is just what data would look like in a kind of grounded situation where the peak is related to the plasma potential. And then if you have an RF driven plasma, you actually get these, the sheet is oscillating sinusoidally, so it gets more complicated. It actually depends also on the mass of the ion. So if you have low frequencies, the ions can react quite strongly to the changing voltages. So you get these really broad bimodal IEDFs. I'll show you in a moment. And if you're using really high frequencies, you get narrow peaks. The problem is with high frequencies, you don't get very much energy. You get a lot of flux. If you apply like 60 megahertz to an electrode, you'd have to apply a huge amount of power to get, thousands of EV energy. So it's low frequencies are better for energy control, high frequencies better for flux control. But the low frequency has a very, very broad distribution. So that's a problem if you want precise energies. Just a more visual version of this, when you have a sinusoidal, first the sheet is oscillating. So this plasma potential is oscillating a bit, or maybe I should say sheet potential. And then there's times when the RF voltage is quite close to the plasma potential and times where it's quite far. So you get lower energy ions and higher energy ions, and then everything in between. So you get these large distributions, okay? With more than one peak energy. And just to show this again, if you try to decouple it, say changing the ICP power, you do mostly increase the flux, but you slightly also increase the energy because the plasma potential is rising. And then in the case where you're just powering the bottom electrode, increasing the power massively increases the energy, okay? And actually, the higher the energy, the more broad the spectrum becomes. So if you're trying to do dielectric etch at 7 kV, 8 kV or something, this is a big problem, okay? So yeah, how do we tackle this, these broad distributions, these drifting things? How do we make it so we're no longer monitoring power? And this is where we get into tailored waveforms, okay? So the idea behind this, I'll show some diagrams in a moment of what it looks like, but the idea is there's kind of two ways of doing it. You can either superimpose several frequencies, so you get different voltage waveforms, okay? So for example, if you want to try this yourself, you could have 400 kilohertz going into the tool and 800 kilohertz, and by changing the phase and amplitudes between those, you actually get quite different waveform shapes, okay? If you're using metal electrodes, I'll explain this in a minute, you can basically use pulse DC to achieve this fine energy control. So you have you might still be at 400 kilohertz, but you have a sharp DC pulse or a longer DC pulse. So I'll show you that in a moment. And by tailoring the waveform, you can actually control what the energy distribution is. And you can do that without changing the plasma chemistry because you're just changing the voltage, okay? You're not trying to impact how much current is there. So usually in tools that have tailored waveform biases, you still apply a different high frequency in order to really get a strong plasma. So like maybe 60 megahertz or 40 megahertz or something to get, and use that to raise or lower the ion flux. So here are just some examples. So here you have like a traditional approach, the 13.56 megahertz. and you see this oscillation. So you go up to the plasma potential, so you're slightly positive sometimes, but most of the time you're negative. You get a large negative average. Grounded, this is showing the plasma potential, basically. And then when an RF bias is applied, you get a split peak. But if you use a tailored waveform, so for example, this shape here, you can get these really narrow distributions, okay? And you can have very precise ion energy control by changing the voltage, simply by changing the voltage here. So when there's a direct link between what voltage you get here and what energy you get here, okay? Now, it gets a bit more complicated than that, like what shape do you use? How does it work in different tools? This is where it gets tricky. Just one thing, if you want to try this yourself at home, for a conductive substrate, you can basically use pulse DC. It's going to be fine. So, so again, this is a sinusoidal waveform, positive, negative voltages. So you have a large constant negative voltage, which will obviously give you constant ion energies, okay? And then you have to quickly do a discharge part of the cycle. So you have to go positive to remove any electron. With a metal electrode, that's not too important, but you do want to go slightly positive and then mostly stay negative in order to tailor your energies, okay? So the energy you get is going to be the plasma potential plus this voltage here, okay? So basically by monitoring the voltage of these tailored waveforms, you're directly monitoring your ion energy, okay? If you're in a dielectric chamber, you have to change the shape a little bit. So what happens is as you pull positive charge down, you are charging up the wafer. So you'll have to compensate for the wafer charge building up for some amount of time. So this slope is helping compensate for that. And then you definitely have to do a discharge cycle where you pull in some electrons to discharge the wafer. And this does have to be tailored a little bit for different chambers and processes. Okay. So this is in general what you got to do. Okay. There's a lot of nice articles out there on this topic. So this is one from Advanced Energy where they show different shapes, different biases, and different results on the ion energies. Okay, but we also want to show this today. Just one other example. This is really nice work from Kessel's group in Eindhoven. So this is just to show how important the ion energies are if you're trying to do something precise like atomic layer etching. So you have the sputtering threshold, as I mentioned before, and then there's a very narrow energy window where atomic layer etching will work. Just keep in mind, whenever you hear atomic layer, think self-limiting process, okay? So you only do one layer at a time. That's what's special about. And then above a certain energy, you're just physically sputtering. You no longer have a self-limiting process, as you have cannonballs hitting a wall, right? And sputtering the materials. And you can see here, you can get very wide peak splitting with the general RF biases. So that means you have some ions in the window doing the work, some ions outside doing nothing, or worse, you could have some ions in the window doing what you want and some doing damage. Okay, so you want to have a single peak. Okay, here's actually there's nice measurements of what these ALE windows are for different materials. So these are things you should kind of keep in your back pocket if you're doing this sort of research. If you do want to try this yourself, there are various suppliers of tailored waveform generators. So a lot of the data, like the data from Kessel's group, was mostly from ProDrive. So they have a shaped waveform bias generator. There's also the Advanced Energy EBOS. Trump-Footinger have some pulse DC power supplies, and Eagle Harbor are also working on tailored waveform supplies. So when we send out these slides, you can check out these links. You can also try this if you just have a signal generator and amplifier. So that's what we have today. We're not sponsored by anybody. So we're going to use just a normal signal generator and an amplifier. And if you're trying this yourself, one hint is to remove the matchbox. Okay. So on the bias side, we care about the voltage. We're not trying to deliver lots of power. We're just trying to control the voltage, at least for these experiments. Okay. So the matchbox distorts the waveform shape. So you set a shape at the generator output, it moves down a transition line. And remember, because you have all these different frequencies, you can even start getting phase shifts just because you have a long transmission line. And then you go through the matchbox, which will have different responses at different frequencies, and it will actually filter certain ones. So if you're trying this, just get rid of the matchbox. And what you should do is apply a high frequency on top like even 13 megahertz will do to strike the plasma and make a strong plasma, and then control the energies using the just the voltage from the signal generator and amplifier. So I'm curious to see what the future is of matching technology based on this. Yeah. So this is the experimental setup. It's almost time for the demo. So we have a capacitively coupled chamber. We have a 13.56 megahertz on top through a match to make it the plasma. And then we have a signal generator, which we're using 400 kilohertz as our base frequency. We have an amplifier. And then after the amplifier, we have an octave, and this octave is just below the electrode. So we have an octave suite. And the octave suite is going to show you what the waveform shape is. So we can directly measure what the waveform shape is and measure what the voltage is during the experiments. And then in the chamber, we have a Semian system, which is going to measure the ion energy distribution function. And we're just using an argon plasma CCP chamber. So this is a very simple research chamber, but I think it will show this. What we're aiming to see today, so this is some data we took on a practice session. We're aiming to show how different waveforms on the electrode will give different ion energies. So at this point, I'm going to come out of this presentation, and we will actually share the screen in the lab. So give me 1 second. Sarah, I'm going to make you the host. Yeah, you're now the host, so you should be able to share your screen. Jordan, is everything ready to go?
Yeah, everything's all good to go. We'll just share the screen now. So first, we have 400 kilohertz sine wave onto the bias electrode. Is that where you want to start?
Yeah. I'll talk to the group through it. So,
sure.
What you're seeing right now is on the left we have the octave software. So we just opened a bit of it, and you can see the RMS voltage. You can see the chamber impedance, which is quite high. Like we're after the matchbox, and we're using a low frequency. We're using, you can see 0.4 megahertz just hidden behind the screen there. So that's 400 kilohertz. And then we're seeing the live waveform. Okay, so right now you can see there's a sinusoidal voltage being applied. Okay, and then you see a distorted current. So that's normal. There's collisions in the plasma and so on. And now on the right-hand side, you can see the Semian software, which is actively collecting the ion energy distribution function data. And what you can see is the average electrode voltage, which is like minus 15 volts. And then you see the kind of typical bimodal 400 kilohertz distribution. So you can see a peak at around, what's that, 80 EV? Yeah, 88, okay. And then there's another peak down near zero. It's probably a bit above the plasma potential, or something like 10 or 15 EV at the lower end. So this is your bimodal IEDF from 400 kilohertz. We're operating at about 2 pascals, so we're a little bit on the collisional side. But anyway, so this is an IEDF with a sine wave, okay? Now, can we switch to a square wave, please? Also, can you go on to last trace in the software so we can see what the shape is now? So you can see we've already dramatically changed the shape just by going to a square wave. Now what we want to do, can we change the duty cycle of the square wave? So we're kind of like in the pulse DC mode. So you can see as we change the duty cycle, you can see the waveform updating. And then you'll also see that we're getting a narrower and narrower ion energy distribution function. So we've gone from a bimodal distribution to a single peak at one energy that's really narrow. Okay, so this is the sort of control you get by doing this sort of tailored waveform. We're in a metal chamber, so we can just basically use pulse DC. If you're in a dielectric chamber, you'd have to have that sloping data that I mentioned, but then all the generators you can buy in the market do that for you. So now we can actually play with the ion energy. Okay, so at the moment, if you look in the octave software, you see we have a slightly positive voltage sometimes. So that's and then we have a large negative bias most of the time. So what we'll do is, if you can show the Semian software again, Sarah, and if we can increase. So what I want to do is, can you place your mouse, Sarah, on the just over where the peak is? Yeah. And what we'll do is we'll raise up the voltage on the output of the pulse DC supply. Yeah, so you can see in the Octave software the voltage is slowly increasing. So we're at 120, 130. Yeah, and you should see now that the peak starts to move upwards. Is the what are we at? We're at 130. Actually, what might be better is if we do an envelope. I don't know. Yeah, that's better. Okay. So can you move the amplitude of the voltage lower and higher, and we'll maybe see the ion peak moving left and right? Yeah. Okay. So we're just going to restart the scan so we clear the screen. Okay, perfect. So at the moment we're at like minus 40, and we're going to minus 50, 60, 70. So we want to, yeah. So now you can see that the energy peak is increasing, but we're still keeping the narrow band. So unlike where if you had a sinusoidal, you actually get broader and broader distributions as you increase the energy. Yep. Now you can see if you look at the Octave data, we're delivering very little power because we don't have any matching. So we're really just applying a direct voltage to the system. So we're only applying a fraction of a watt. But the 13.56 megahertz on top is what's really driving this plasma. And it's that simple. So what the Octave is doing at the moment, so the Octave is measuring the voltage and current waveforms right at the base of the electrode, okay? Which is a little bit different than what we're applying at the signal generator. So at the signal generator, we're outputting basically a square wave. And the way we're slightly matching is that we have quite a long transmission line. So we are seeing, not a perfect square wave. We're seeing kind of like a peak. Well, basically, whatever you apply on the signal generator, you'll be able to see in real time on the Octave suite. So whatever your shape happens to be, it will detect it, but it will detect what the shape really is. Like you can take this measurement right up against the electrode. So you can see what's really making it from the generator to the electrode. The reason why that's important is, if you design a specific shape that works for your process, that shape doesn't like to get a specific energy. That shape is not what necessarily makes it the electrode. It is the same issue as, if you apply certain power at the generator, by the time it gets to the electrode, it's, slightly less power. So, so in tailored waveform applications, you do need this feedback loop, like closed loop feedback from what's on the electrode. Now, the Octave is quite close to the electrode. There's maybe 10 centimeters maybe 15 centimeters from the sensor output to the electrode surface. There is a thing you can do called an impedance transformation, where you can you basically take some measurements of the network between where the sensor is and the electrode surface, and you can use that to transform the data to what it would be on the electrode surface. So that's something we know how to do. We've actually done on another chamber, so we can measure exactly what's on the surface as opposed to at the distance. So you can use the Octave suite for this live feedback control. Yeah. What might be worth doing, Jordan and Sarah, is if you go to maybe raise the energy up, raise the voltage up to as high as we can go without the reflected power causing damage to the generator, and we switch back to sine wave, and then we'll see the bimodal shape going back or something like that. Yeah, so you can actually see the split peaks coming back now. Yeah, and now you have the high energy peak and the low energy peak again. So, yeah, that's it. So if you had the electrode transformation done, what you actually see is the voltage that you measure and the ion energy are almost, so let's say you have a plasma potential of 20 volts. I actually have this data on the screen, so I'll swap back. So thanks very much, Jordan and Sarah, for showing this. I'll put the slides back up to show. Sure. So if you look at this data here that we collected last time, so this was done when we had the transformation, and you can see that the the voltage that we're getting on the sensor was minus 50 volts, okay? And the ion energy we're getting is 70 volts. And on this chamber, the plasma potential is 20. So you can actually get a direct measurement of what the ion energy is in that case, basically, as long as you know the plasma potential. But the plasma potential, as you've seen earlier, does not shift for too much. It only shifts a few EV as you change the top power. So yeah, so it's that easy to do. And you can see with our sensors, you can get live feedback on what's happening as you change these parameters. Yeah, at this point, we can actually we can go to Q&A. So the sensors we're using today, again, we use the Semion sensor, which was in directly measuring the ion energy distribution function, and the VDC, which was on the electrode, the average VDC on the surface. And we're using an octave suite, although we're using this shape in order to measure the voltages, the currents, the waveforms, and the power. Yeah, and I should mention as well, because the octave suite is measuring the voltage, current, phase of all the different harmonics that are used to make up the waveform, we can actually look at the power delivered. So if you are trying to maximize the power delivery into the bottom electrode, we can measure that. Okay, so I will check on the questions. First question is, how is power being measured? So a VI probe has a voltage and current pickup that are beside each other. So it measures the voltage and current at the same time, and then also the phase. So we're just measuring voltage times current times the cosine of the phase. Now the power value that you were seeing in the software was actually just the power in the fundamental, the 400 kilohertz sine wave component of the tailored waveform. You'd have to add up you have to look at the total power of all the harmonics in order to know the total power delivered. We didn't show that today. But yeah, just voltage times current times the cosine of the phase is power in this case. Oxen is asking, what happens to ion energies if you increase the duty cycle of the negative portion of the output? Can we try and see in real time? Okay, we might be able to go back. If everything's still running, Jordan, we can maybe jump back in a few minutes. How do we decide the bias frequency? It's a good question. So you want to use the lowest frequency possible, basically, because the higher the frequency you use, basically the more, like the high frequency couples well into the plasma. Okay, so it might be best. I actually don't have frequency versus results in this presentation, but as a rule of thumb, if you want to control plasma density, you use the higher frequencies, okay? Because you get the most inductive coupling, which is more efficient at generating plasma, whereas at the low frequencies you get more capacitive coupling, okay? So even if you're in a CCP, as you operate at higher frequencies, you actually have quite a large inductive component, and the inductive component makes it like an ICP. You get much more dense plasma. So higher frequencies more inductive, lower frequencies more capacitive. So you want to use low frequencies for that. That's one reason, and the other reason is at lower frequencies the ions can respond more to the voltage. Okay, so that means that you can get the ions to go all the way up to the peak energy. Okay, whereas at higher frequencies you're pretty much only going to get the average voltage as the ion energy. But yeah, so at low frequencies you can get all the way to the peak energy, which is going to be 2.8 times the RMS voltage. So you get much higher energies at lower frequencies. So you should use something like we use 400 kilohertz because we have that. We even have Matchbox available at that. You should use 200 or 100 if it's available. Just again at those low frequencies as well, you have really high chamber impedances. So you saw we were at like a kilo ohm impedance for our chamber at that frequency. So that's the other limitation. So you maybe don't go too low if you can't get any power in. Yeah, that's how we choose that. The figure left, the negative pulse. So David asked, the figure left, the negative pulse is very short compared to the positive pulse. Does the duty factor matter? Yes, actually. we might be able to go back and do some live, we show that live. Anonymous asked, can you make IEDF measurements on both powered and grounded electrodes? Yes, so we can, the Semion will work on any electrode. It doesn't matter if it's powered or not. So you saw there we are directly on a powered electrode. We can put it on 13.56. We can put it on 60, like whatever you can, it will work. Charles asked, does the probe add parasitic to the voltage circuit that affects the measurement accuracy? And when the Semion probe is removed, will the IED be the same, although we cannot see it? Good question. So usually when we install a probe after the matchbox on a tool, we usually aim to replace a section of the transmission line. So that's the first thing, because we don't want to change the distance if possible. Also, our sensor has an air core, so it has a speed of light of 1, whereas if you're using a cable, it's like speed of light 0.7 C or something like that. So so one thing is you want to make sure the electrical length is the same, right? From our experience like putting these sensors in, they do add a few picofarads of capacitance. But otherwise, like it's not like a directional coupler. It's a voltage and current pickup, which are some distance from a rod, and we're just sensing what the electric and magnetic fields are. So we're not drawing any significant power. Like I know a directional coupler might draw a watt or 2 watts or something, but if you like it, the tiniest fraction of a milliwatt or whatever will be drained by the remote sourcing. So so yeah, we do add a little bit of capacitance when we put it in line, but not so much to affect majorly affect the transmission line. Usually, actually, worst case I've seen when retrofitting these into production tools, the matchbox might move 1 extra tick. Now, when the Semion probe is removed, will the IED be the same? So this is a good question. So not exactly, but pretty close. There's 2 things to consider when you add a Semion. I'll actually go back and show you, because I have a I have to go back to the first slide, actually. When a Semion sits in the system, there's 2 things that it's changing a little bit. Let's go back to slide 1. Nearly there. So there you go. So this is an actual picture of a Semion inside our plasma chamber. So the not actually the one on the call, but this is another one in our lab. And you can see, so when you put a Semion in, it's 5 millimeters thick. So you are raising your electrode 5 millimeters. Now in our chambers, which have a very massive distance between the CCPs, it's a completely negligible thing. If you have maybe 20 millimeter gap or something between 2 electrodes, it is more significantly changing the geometry, which may change the plasma potential a little bit. So one thing to note is the distance change, but in general, it's negligible. In the majority of tools, it's a negligible change. The other thing is, so the Semion, in order to take measurements, there's wires going out to ground. We put really high impedance filters between there and the measurement circuit, about 200 kilo ohms typically, something like that. So we, an ideal RFEA has infinite impedance to ground, so we do not load the electrode at all. In reality, in order to still get a measurement, they're about 200 kilo ohms, so we do load the electrode a little bit. But again, I suspect that's like a kind of 1 or 2 EV change, not a major change. The shape is certainly still the same. The energy should be pretty much identical. We have seen from some clients where they have full simulations of what's going on in their chamber that the Semion system does match the simulations. So next question. Do you mask measurements during the off phase, or is it averaged through the full pulse cycle? When we're measuring with the Semion, it's just a time average measurement we're doing. We do have a system called the Semion PDC, which can do time resolved measurements. So if you have pulse DC, you can actually get these time resolved IDFs. So you can actually see the voltage raise up and the voltage or down, and the energies, on the nanosecond time scale. So the sensor we're using today was just pure time average, but we do actually have time resolved sensors available for time resolved IDFs. Matches are generally directly connected to the chamber. How do you overcome this connection? So you mean putting in the octave sensor? And now in air chamber, it's very easy. We have a cable before and after the match, so we just put it in as a extra on the cable. Where they're directly connected, to be honest, in those cases, we have ended up moving the match down some length. What we actually really try to do is usually the match has a kind of output rod, so there's the inductor ends and then there's like a length, and then there's like another length where there's like a mating part that goes into the tool. So we've tried to make sensors that replace the section from just after the inductor to where the chamber is without changing too much. So almost like slots through the match is one option, or just inside the match. But if all else fails, ultimately you do have to move the match a little distance. We do have sensors. I don't have images in this presentation, but we do have sensors which are shaped such that they can mate with like the Advanced Energy Navigator 2 or some of the other common matchboxes that are out there. And we have special adapters for some of our sensors for specific tools like the AMAT Sim 3 or some other, some common tools. So do send me an email if you're looking into integrating into your tool. We may already have a solution. Charles, thanks for the presentation. No problem. So Jordan, is everything still up and running? Maybe we can play a little bit with the duty cycle. Can't hear you, sorry. I saw you unmuted, but I can't hear you. Okay, sounds not coming through. If you send me a message, in Teams, I'll check. Another question came in. Sorry, 1 second. David asked, with the loading of the semi-electrodes, effect measurements of very low ion energy, can this be resolved by the software? I know that the minimal energy resolution will need in the software. So actually, the Semian should have 0.1 EV resolution. You can actually do 0.1. We use 0.1 voltage supplies. We do have some clients who do very, very precise measurements at the 1 to 5 EV range. We have not seen an issue, although in those cases they were kind of ion beam, effectively. Okay, it's all set up and running. So I'm going to stop sharing my screen. And Sarah, do you want to share your screen and we'll try the different duty cycles? Yeah, so you can do 0.1 EV, David, with the Semian. Yeah, we have clients who use these for low energy measurements. I can send you some papers. Send me an email and I can send you some nice papers where they've done precise low ion energy measurements. The only thing you have to worry about with the Semian with low ion energy measurements, if you have really high ion flux, there may be a voltage drop across those 200 kilo ohm resistors, which will change the data by up to 1 EV. We can help correct that, or our quantum system can actually measure before the resistors. You get more precise at lower energies there. Okay, so we have the screen shared again. So yeah, do you want to play with the duty cycles maybe, and let's see what happens to the IDF? We're at 50% duty cycle now, I think. Are we able to go all the way to 90? Aha, there we go. So what's happening here is with the, I think this is what I just saw. So with 400 kilohertz, you have a bimodal distribution and you have 2 different peaks. So I think by playing with the duty cycle, we're actually activating which one of the 2 peaks we see. So if we go back to 5% duty cycle and keep the voltage the same, we're probably going to have the high energy peak, right? And in this case, we have the low energy peak. What might be good is if we restart the scan and use envelope mode and slowly increase the duty cycle, so we see we give it enough time to do it as an IDF scan. So this is, I want to say, this is the nice thing about our instruments, right? You get really live feedback on exactly what you're doing, right? So, yeah, do keep on going. And then what I reckon is after we reach 95%, can you go back to sine wave and we'll see how it superimposes over everything there. And we let the sine wave run a little bit. Yeah, okay. So it looks like we are basically shifting between the two different peaks that were available at 400 kilohertz. Yep. And by going to the different duty cycle, we're able to reach more of the peak energy, less of the average energy. So I reckon if we were down at 100 kilohertz, you'd be able to go all the way up to the the highest voltage that you see in the octave, is what I think. Yeah. So there you go. Okay. So I think are there any other questions? Yeah, so there's also ways of changing the ion current. Now, for this demo, we just wanted to show the energy changing, but there are also ways of playing with the ion flux. Okay, if I see no more questions coming in, we can end this early. Thanks everybody for attending, and we will send out the video and the slides shortly afterwards. And yeah, please feel free to send me an email or info@impedans.com or something, and we'll get back to you with any other questions people have. All right. Thank you very much, everybody. Bye-bye.